Hello everyone, this is Professor Iris Miano. We are in day 3 of Math 2 Pre-Calculus. I will be covering 3 sections, and they will be starting with section 1.3 on properties of functions. We will also be talking about piecewise defined functions in 1.4 and graphing transformations in 1.5. And here we go. Let's go ahead and talk about first what it means to be either even or odd for a function. Of course, it's possible to be neither even nor odd, but if you're even, then you are going to be, as a function, having your input values, whether they are some value of x or its opposite, it's going to give the same exact output. And a good example of this visually is a standard parabola or squared function. As you can see in the picture, one way that you can tell visually if a function is even is if you could fold it over the y-axis, you would have the trajectories lying directly on top of each other. So in this case, for this definition, well, let's go ahead and say that we are going to call it even. Okay, now what does it mean when your function is odd? Well, an odd function, and here we have a quintessential example in the cubic function, or y equals x cubed. The way you can see it visually is pretend that the center of your graphical representation is the center of a spinner. And if you were to spin the line created by the graph 180 degrees, you would line it up exactly with how the original graph looked. And algebraically, if you have a negative input value coming in, it's kind of like that negative sign transfers its way out in regard to the output value on the other side of the equation. So yeah, so you'll see examples of that when you get into the homework on how algebraically you'll find that a function is odd. There we go. Moving on to other visual representations of functions. They can be increasing, decreasing, or constant for the entire function or on specific intervals. So here in this first figure, part A, and by the way, I got these figures from your book. The other figures previously I just lifted them off the internet. So here is an example of an increasing function. So I'll go ahead and put increasing in the blank. And the way that you know it's increasing is that as you increase your x values, so if x2 is greater than x1, like we see here in the formal definition, then also the corresponding output values also increase in the same manner, okay? Graphically, you'll see your trajectory rising as you scan the coordinate plane from left to right. Now, if your function's decreasing, like in this next figure, you'll notice that as you increase x, your function outputs are decreasing, and you have the algebraic representation here as well. Certainly, you can be neither increasing nor decreasing, and then in that regard, you would be constant. As we can see in the figure, we just have a horizontal trajectory, at least for some piece of the domain, and the output is exactly the same for any value in the domain within the specified interval. Okay, cool. So when you have a series of increases and decreases going on in your function, it might behoove you to talk about maximums and minimums, and there's a difference between locals and the absolute. So I have a bunch of text, as you can see on the screen and on your corresponding lecture handout, that is pretty much straight out of the book. I want to have definitely formal definitions at your disposal in case you haven't yet gotten your hands on a book and you want to read what the book has to say about that. And also I want to give you my overall understanding of what is going on for maximum and minimum values, local versus absolute, because the way they're defined in the textbook is incredibly similar and a little bit confusing. So let me just kind of get you oriented on what you see on the screen. If we're just focusing on a maybe relatively small open interval of the domain, then the value will be called a local maximum. So that's the first two blanks you want to fill in. If as long as you have a largest output with relatively smaller outputs in the local vicinity. And if you want to see what we're talking about in the formal definition, I would look starting right here, which reads as follows. A function f has a local maximum at c if there's an open interval I containing c such that for all x in that open interval, you're going to have your outputs be the maximum at that c value, and then all of the other outputs are less than that, okay? So then you would call f of c a local maximum. And then there's a formal definition, if you're reading ahead, starting right here, of an absolute maximum, which you will find to have pretty much the same wording, except for c changed into a u. So I find that to be a little bit confusingly similar. And then we have these other formal definitions for local minimum. I'll just go ahead and fill those in. And absolute minimum. And so just so that we're all clear about the differences between these, your graphical representation of your function could exhibit several different points at which it has peaks and valleys, the peaks being the maximums and the valleys being minimums. And so all of the maximums are considered to be local maximums, but the highest among all of them within some open interval is called the absolute maximum, and the same can be said about local minimums versus the absolute minimum as far as valleys are concerned in your in your graphical representation. We're going to see some pictures in just a moment. I just wanted to address what I find to be confusing about the formal definitions and how they are just, here I'll highlight it, confusingly similar. But really the thing you'll want to just keep in mind is that there can be local maximums and minimums, several of them, but there's only one absolute. Okay, that's the main difference between those two terms. And furthermore, the absolute maximum or minimum also is considered to be a-local, but it is the highest peak or the lowest valley if it's going to be categorized as an absolute. And so that leads us to the definition of the extreme value theorem, which is if f is a continuous function whose domain is on a closed interval from a to b, and f has an absolute maximum, then f has an absolute maximum and an absolute minimum on AB. It's supposed to say then right there. So let me fix that typo in real time. Here we go. And of course, you have some blanks to fill in. And what are the blanks? Extreme value theorem. All right. So there you go. Great. Moving on to average rate of change in secant line. These are the last two ideas, and they're kind of mixed up into the same idea as far as I can see it in regard to wrapping up 1.3, and then we'll go into some practice exercises together. Okay, so the only thing you really need to know about the average rate of change is it's basically the slope formula. In fact, it's exactly the slope formula if you have ordered pairs a, comma, function output at a, or b, comma, the function's output at b. So these are ordered pairs likened to x and y. So here's x1, y1, x2, y2, as you have formally been introduced to the slope formula. And yeah, you put it all together in the way that you understand the slope formula to be constructed, and there you go. So if you ever want to find the equation of a secant line, of a function, you just need to pick 2 points on that function and find the slope between those 2 points, and then use one of the points in the point slope formula, and there's the equation of the secant line. Okay, great. So I'm just going to blurt that out real quick and then allow us to move forward into exercises. So you'll notice I have problems 13 through 24, and I just lifted this straight out of the book, and it corresponds to the following figure that you see to the right with the blue trajectory. Several points are plotted, and we're going to use this visual in order to answer these several questions. Okay, so I'm going to change up the color every time I get into a new problem. So is f increasing on the interval from -8 to -2? This is number 13, so I'll put a little blue dot there. Let's see. Well, let's take a look at the interval from -8 to -2, and we're talking about the x values. Okay, so from -8 to -2, are we indeed increasing? Yes, we are. If you'll notice, as I start from -8 and then move my cursor over the trajectory to x equals -2, indeed I lifted it up in an upward direction, so we would say yes. Okay, change the color for a new problem. Let's do this orange color. Is f decreasing on the interval from -8 to -4? Okay, again, starting at -8, go to -4. Was I decreasing at any point when I did my cursor traveling? Let's see. Try it one more time. Here I'm at -8. I'm going up, 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 up to -4. At no point was I decreasing, so nope. And really you have to be decreasing the whole time in order to categorize it as decreasing. Change the color. Let's go with this magenta. Number 15. Is f increasing on the interval from -2 to 6? Okay, here's -2, and then we are going to go down. So yes, I'm decreasing, but wait, I'm only at 0 here, and I'm supposed to travel all the way to 6. So I'm decreasing here, but then I'm increasing again, decreasing again, and then increasing a little bit more. So would you say that I was decreasing on that interval during some of it, but not on the entire interval? So we would say no. Okay. Next question, number 17. Or sorry, we're on number 16 now, excuse me. Are we decreasing on the interval from 2 to 5? Start at 2 and then travel to 5. Boop. Yep, I was decreasing the entire time, so I would say yes. Okay, great. Here we go, new color, new problem. Number 17, list the intervals on which f is increasing. Okay, so I'm going to mark in green all of the times on which f is increasing. So like we saw earlier through some of this investigation that we were increasing from -8 all the way up to 2. And then also look again for the rest of the trajectory. It looks like we're increasing also from 0 to 2. And then lastly from 5 to 7. Okay, so list all those intervals and include the endpoints, okay? So that'll be, again, from -8 to -2, from 0 to 2, and then from 5 to 7. Okay, new color. Let's go with this dark blue. And let's list, oh, actually, I want to pick a different color. Let's go, we haven't done red yet, just to make it really contrast from the colors that are already there. List all the intervals in which it's decreasing. So I'm going to go ahead and decrease trajectory trace here. And it looks like it's all of these portions. So that'll be from -10 to -8. From -2 to 0, from 2 to 5. Cool. All right. Moving right along, we'll do the light green next. Is there a local maximum at 2? If yes, what is it? Okay, local maximum at 2. Let's go to 2. Yeah, it looks like that is indeed a local maximum. So, and what is the value at that local maximum? It's 10, the output. So I would say yes. I'm going to circle it and go yes at 10. All right, is there a local maximum at 5? What do you think? Does that seem to be associated with a peak that's going on here? No, I would say that that's associated with what I would call a valley at 5. So I would say no. Just a straight up no to number 20. Let me just go ahead and put a little dot there. What's a new color that I can use? How about this pink color? I don't think I've used yet. So I would say no. And I mean, we could circle. Nah, I won't even touch that one. Okay, now for number 21, it says list the numbers at which f has a local maximum, or the local, and what are the local maximum values. So we're going to look for all of the peaks, basically. All right, use the light blue. All of the peaks are occurring here and here. And then, so they are happening at -2 is where the local max is happening, and the value is 6 there. And then another local max is happening at 2, and the value is 10. So I'll use LM as a shorthand for local maximum, and the value, local maximum value, V, is going to be happening there as well. Okay, so cool. Great. Moving on, so that was in this light blue color. Let's change the color once again. Ooh, we're running out of colors to rely on. Have I not used this one technically, which they're calling plum? I don't think I've used that one yet. Okay, great. Let's use that one here. Local minimums. So we're going to look for all of our values here, which will be here, there, and there. Okay? All of the points in which you dip down and you recognize that, at least in the immediate vicinity, most of all the other points on the trajectory are greater than those particular values. So the local minimum, which is the same letters, is happening, there's 3 of them, at -8, and then their corresponding values, put next to it, -4 for the value. The local minimum here is at 0 and its value is 0, and then the local minimum as 5, its value is also a 0. Okay, cool. Find the absolute minimum on this entire trajectory. So that'll be, I'll put that in, I guess, gray. Absolute minimum is going to be the lowest point ever. Now that's this one right here, is going to be the absolute minimum value, and they do it when they do the answer in the book. So the way that they want you to present it is f at -8, and so the value of it is going to be -4, the output. Okay, lastly, what's the absolute maximum? Boop-a-doop-a-doo. Have I done this yellow color yet? I have not. Okay, let's do that one. So that's going to be this tippity top peak. So it's f at 2, and the output value is at 10. Okay, great. So hopefully that's all meshing well in everybody's minds. Let me know if you have any questions about that. Moving on, though. Okay, so let's go ahead and look at these graphs, number 25 through 28, and try and find the intercepts, domain range, intervals on which it's increasing, decreasing, or constant, and categorize it as either even, odd, or neither. Yeah, that's an important point that I want to make, that not all functions are either even or odd. Sometimes they're neither. Okay, so let's start with the intercepts, and we're going to do them rapid fire for all 4 of the problems at once, parts A, B, C, and D, that is. So we'll do part A in yellow, and do, we'll do it yellow for x-intercepts, and then we'll do, I don't know, this pink color for y-intercepts. So let's start with the x-intercepts, if any. So x-intercepts happening are at these points for number 25, these points for number 26. There is no x-intercept for 27, but here's the x-intercept for 28. Okay, now for y-intercepts, They are occurring whenever you cross the y-axis, which is happening here, 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 and not happening at all for number 28. Cool. So I'll put another colorful dot there. Now switch up the color scheme. Let's talk about domain and range. Now the domain is going to be, I'll do that in green, and I'll write it directly underneath. The domain is going to be all of the x values that you see spanning here. So as far left as it goes, it looks like it's -4, so I'll use the set notation x such that it goes from -4 to +4. So I'm going to write a compound inequality including the endpoints. Here the domain is very similar, -3 to 3, including those endpoints. Here the domain appears to be all real numbers because these trajectories have arrow points at the ends, and they're going to go off to positive and negative infinity. So here the domain is all reals, or you can do parentheses with negative infinity to positive infinity, comma in the middle. I would say the domain here is also all reals. Okay, now let's do the range. That's all the y values that you expect to be appropriate here. So I'll put red for that. So the range is going to be, what y values do we span? Well, the smallest y value appears to be at 0. And I go all the way up to 3. The range for number 26, same. Start, the lowest point is at 0, go all the way up to 3. Okay. Here the range appears to be all reals. Range is all reals. Range here also all reals. Oh, wait, hold on. The domain, all x values, yes, is all reals. The range, it looks like we are following an asymptote. I'm so sorry, I misspoke. Let me go ahead and erase this bit. Talk about, oh, and I believe I misspoke on the domain on this first one. Yikes, guys, this is what happens when I rush. Let's go back to the domain discussion on number 28. It looks like we are writing the y-axis as an asymptote, something that we haven't formally defined in this course yet, but you may have already been introduced to. So it looks like we are, x has to be strictly greater than 0 because we're not going to cross the y-axis is the indication that we have. Like, that's the implication that we have here. So x such that x is greater than 0 strictly. Okay, there we go. Sorry about that. Now going back to the range discussion for number 27, it looks like we are never going to cross the y-axis, so the range therefore will be y such that y is greater than 0. Cool, but for the range here, we seem to be spanning all of the possible values of y, so the range will be all reals. Okay, whew, crisis averted on that one. What are the intervals on which the function is increasing, decreasing, or constant? So I'll go ahead and say increasing is going to be, oh sorry, let me do a not so similar color. Let's do the blue. Nope, we need something a little different. Increasing will be orange, decreasing will be the dark blue, and constant will be in light green. Okay, so where is it increasing? For this first, for number 25, it appears to be increasing here and there. So you can note the intervals accordingly and make sure that they are closed intervals. We're increasing here. The entirety of this trajectory seems to be increasing. Same here. All right, always going to be going up as far as the x value is concerned. We are decreasing, let's see, where's that blue color? Here and there, and there, and at no point in numbers 27 and 28, and at no point are we constant as far as the series of values is concerned for any of the 4 examples there, so we won't have any of those light blue instances. Now in this dark purple, we'll go ahead and categorize each as either even. So I would say that number 25 is even because you could fold it on the y-axis and have the trajectories line up. Same with number 26. Now 27 and 28, neither of them have either y-axis folding symmetry or origin rotational symmetry, so we would say neither for both of those. Neither. Great. Okay, moving on. Average rate of change. Yes, let's practice using that formula real quick. So notice that our function is negative x to the third power plus 1, and we're going to try and find the average rate of change from 0 to 2, from 1 to 3, and from -1 to 1. Now this is relatively quick if you know the shortcut. So from 0 to 2, right, the ordered pair is the thing you want to grab for each of those two locations. 0 and 2 each being separate inputs. So if 0 is the input, plug in 0 to your function, and what do you get? Well, you get the output as being 1 because this little guy zeroes out. So the ordered pair here, when the input is 0, the ordered pair is 0, 1. When the input is 2, the ordered pair is 2, -7. How did I get -7? Well, you plug in 2 into x here, you cube it to get 8, you negate it to get -8, and then you add a +1 to it. -7 is what you get there. So then you plug in this into your slope formula, basically. So -7 minus 1 in the numerator, 2 minus 0 in the denominator. That gives you -8 over 2, which settles down to a -4. And that's your final answer for that one. Okay, we could do this 2 more times relatively quickly. All right, so if we're going 1 and 3 as our different inputs, the ordered pair for 1 is going to be 1, 0. Plug in a 1 for x and you should get 0 as your output. And the ordered pair at 3 is 3, -27, or sorry, -26 rather. Okay, and then find the slope in between those 2 points, -26 minus 0, 3 minus 1, right, is one way to do it. And you'll get -26 over +2, which gives you -13. Okay, one more time, and then we'll be done with this. All right, let's plug this in. -1 and 1 are 2 inputs. When -1 is the input, 2 is the output, so that's the ordered pair -1, 2. And this one we already did, it's 1, 0, right? Find the slope there. Slope and rate of change, same thing. 0 minus 2 in the numerator. 1 minus a -1 in the denominator. Go ahead and make sure you do the double negativity adjustment there, and you should get -2 over 2, which settles down to -1. Cool. So a little bit of algebraic practice there, rapid fire. Hopefully that was all very familiar. Okay, I think we're ready to move on to the next section here, library of functions and piecewise defined functions. So this is where we get to know some real famous functions. These are the celebrities of the function world, and we need to get to know them because in the next section we're going to deal with slight manipulations of them, and recognizing those manipulations we'll be able to see how to come up with the functions, and they're going to be very much based off of these parent functions. Okay, so here's the first one, a constant function. It's a horizontal line. It comes in the form of y equals some real number, or rather f of x, because we're dealing with function notation now. Here is some pertinent information about this particular function: domain, range, where it increases, where it decreases, and then concave up, concave down. That's something that we haven't really talked about too formally, but if you have any experience with parabolas and then quadratic functions in general, you know what that's up. Concave up is basically a U-shaped trajectory. Concave down is more like an arch-shaped directory. Anyway, so there's the constant function. Here's the identity function, which is likened to y equals x. It goes through the origin. It's increasing the entire time, never decreasing. The domain and range is all real numbers. Yeah, and there's no concavity of any kind. the square function, f of x equals x squared, super famous. It's just your quintessential parabola. Here's your domain, here's your range. It's increasing on the, in the first quadrant, decreasing in the second quadrant. What else can I say? Concave up the whole time. And because the leading coefficient is positive. We'll talk about that more when we get into 1.5 when it's negative, what to do. All right, then there's the cubic function, or the cube function, as it's called here. And here is all of the pertinent information there. Here's what the trajectory looks. It kind of looks like a parabola, but with one of the edges kind of twisted downward, so to speak. But then again, some of these places where you have points are not exactly lining up because we are dealing with the cubic. So it's not exactly the same. The square root function kind of looks like half a parabola on its side, and that's no mistake. It's definitely related to the classic parabola shape in the square function. And here's the pertinent information there. Notice in particular the domain, okay? Only positive values and 0 are allowed to go into the function because of the square root nature of the function itself, okay? And there you go. Cube root function, okay? So that's going to be looking like your cubic function but on its side. And that's because they are indeed related. And here's some pertinent information there in regard to its structure. The reciprocal function, 1 over x. Okay, the interesting thing about this one is that we have these two dashed lines as a part of the representation, and that is to show you the asymptotes. There's a horizontal and a vertical asymptote at the x and y axes respectively. So that means the trajectories will not be crossing the x or the y axis ever. So there's no intercepts. The domain has, and the range has this little hole at 0. It is never increasing, always decreasing, but of course we have to leave out the point at 0. Yeah, and then the concave up, concave down areas are listed here. Cool. And then there's also the absolute value function. So this is your V-shaped function, and you will notice that it never occurs anywhere in the below the x-axis. It's always on top. But that is to say that the parent function only occurs up top. And by up top I mean in quadrants 1 and 2. If you were to flip it over, and this is stuff we'll get into in 1.5 with a negative coefficient, then of course it would be occurring in quadrants 3 and 4. I don't need to mention that. That's something that we're going to get into, like I said, in the next section. Okay, so you'll want to get to know those functions, and also this very famous piecewise defined function, the greatest integer or step function. So that has a particular structure that I wanted you guys to write in to the blank here. So this would be f of x. Oops, let me go ahead and change my drawer, and I'll go ahead and change the color to this beautiful purpley kind of magenta color, and I'll also erase what I put here. Okay, so it's f of x is called, it's a special int function, int of x, which is just to say it's the greatest integer less than or equal to x. I'll write that in, greatest integer less than or equal to x. Okay, and here's a graphic that I lifted from your textbook. Notice that the black points are going to be, those are meant to act as solid points. And then you have the trajectory in blue. So all of that is part of the output possibilities. And then the white dot is meant to be like the bound on where each blue trajectory ends before it picks up again at the next integer value up in the function output sense, okay? So there's no overlap in as far as the value is concerned between the white and the black dots. I mean, they overlap certainly if you were to put a vertical line there, so you're thinking, oh, violates the vertical line test, but remember, the white or the open dots are missing a value. It's like just supposed to be representing the edge of the value that's exhibited by the blue trajectory. It's not actually included in the function itself. So that's why this piecewise defined relation is indeed a function. Okay, great. So then there are other piecewise functions that you can create. And so notice in figure 42, which again I also lifted from your book, it has this function representation here. Okay, so notice that there are different pieces of it that just get connected together. So it's like if you had 2x plus 3, which is this increasing, right, trajectory right here, but you only graphed it up until x is 0, and you grabbed everything x being less than 0, right? So as far as going off, starting off from negative infinity and approaching 0, you're going to be modeling that via this line right here. And then once you hit x equals 0, you need to have the rest of your trajectory follow this other line right here, a decreasing line. So it has, you know, this negative slope here, but it has the same y-intercept, so that's where the overlap happens. So the y-intercept is technically just associated with this piece, the second part of the piecewise function, because that's where x is included to be 0. Okay, so hopefully that kind of makes sense, like what's being represented here and how it relates to the function as it's being defined here algebraically. Okay, great. So I wanted to put together one exercise with you. Here's a coordinate plane that I'm providing for you, and off to the side I have this line, this closed dot, and this open dot in order to put together the graph for part C of the exercise. Okay, yeah, and so this is from number 31 from the textbook homework set. Yeah, so let's go ahead and tackle all of these little bits. So the first thing is to find the domain of the function. Okay, it says each function because these are the blanket directions for many exercises, but yeah, we're just going to focus on this one. So the function has an output of either 2x or 1, depending on if x is equal to 0 or not, irrespectively, okay? And so since the domain can either be equal to 0 or not, that together collectively captures all real numbers. So I'll say for this first one, the domain would be all real numbers. I'll just kind of put the fancy R there to indicate that. All right, now we're going to locate any intercepts. Now intercepts are when either the x or the y value equals 0. So when can x equal 0? Well, when x equals 0, and I'm going to change the color here to work on a different thing for part B, x equals 0, right? That's going to give you your y-intercept. So the y-intercept is going to be at 0, -1, okay? And then is there an x-intercept? Good question. Well, the x-intercept would occur when the function's output is equal to 0. Now, can the function actually equal 0? Well, think about it. When would this ever equal 0? Well, when the x value is 0. But wait, that part of the function is designated for when x is not equal to 0. So we can't plug in 0 into here. When x equals 0, the output is 1. So that means that the function can never take on a value of 0 as its output. So there is technically no x-intercept. I know, kind of mind-boggling. So there we go. We have the only intercept. There's a 1 y-intercept at 0, 1. And then we're going to graph this function. So I cheated a little bit and came up with the line that has a slope of 2, and it's going to go through the origin. So this is just your regular run-of-the-mill y equals 2x, or f of x equals 2x, right? But remember, when x equals 0, which is right here, we actually do not have a value. So I have an open dot that I'm just going to line up real nicely here. Okay, so now here's my open dot at x equals 0. And then, so when when x does equal 0, then the output value is going to be 1. So at 0, 1, that's going to be my y-intercept. So I'll just go ahead and line that up as best as I can, right about there, 0, 1. Okay, so then there makes up my graph, okay? So when you're doing this kind of stuff by hand, I recommend that you use a straight edge to make your straight line trajectories really super pretty. Whenever possible. Okay, so I did this in kind of like a blue color, the graph. Oh, whoops, hold up. Why is it being strange with me? I want to draw with blue. Hold on just a second, guys. Oh. Okay. Okay, so in any event, I think we are ready to talk about the range. Now the range is going to be everything, like all y values are possible with the exception of 0, right? So if we wanted to do that, hold on just a moment. Let me see if I can figure out what the deal is here. Why it's, okay. It's doing a strange thing here. Let me just pause the recording and see if I can figure out why it's doing that. Just a moment, guys. Okay, we're back. I don't know what the deal was there, but in any event, we just want to do the range, right? Which is to say that we are saying that all of the possible output values are everything except for 0. We cannot have an output of 0. So we'll say that it's y such that y cannot equal 0. And that's good. That's a way to do it. Okay, great. Moving on. All right, we're in the home stretch here. I know you've already been listening for about 40 minutes. Good on you. Feel free to pressing pause and taking little breaks throughout if it's conducive to your learning. Now, I've gone ahead and lifted a giant table from your textbook, which is a really great collective overview of all of the different techniques that you need to learn in order to identify shifts, stretching, compressing, reflection, all of these types of things in regard to transformations, okay? So the easiest ones to spot are the vertical and horizontal shifts, but they can be pretty tricky as far as like in what direction to go based on the structure. So notice that your vertical shifts are always going to be when there are constant values either added or subtracted away from the actual function. So what does that mean? It's just if you have an added or subtracted value that's separate from whatever's being initially or more closely imposed on x, like if it's directly on x, then you have a horizontal shift, okay? And it's very a little bit backward in my understanding. Like the way that I learned it was just to say, okay, when there's a value added to x directly and it's a horizontal shift, if I'm identifying it and I know that to be true, then it's going to be moving to the left, okay, which is a little bit counterintuitive. If you're like, oh, I'm adding to x, I should be getting bigger in x, which is moving to the right. Oh no, please don't do that. Recognize that when you add a value to x, you are shifting to the left. And then if you're subtracting off a value directly from x, you're shifting to the right. If it's indirect on x, the added value, it's a little bit more intuitive. That would be when you're adding k, for instance, you're going to lift the graph up by k units. And if you're subtracting off, you lower it. So you shift it down. Now, compressing and stretching can be a little bit counterintuitive as well. So if you have a being multiplied directly on the function output or the function input, then you're going to be doing the opposite things here. So if it's directly on the function output, then you'll have, if a is greater than 1, you'll be stretching items, so making them wider, and then you'll be compressing them, making them smaller or seem skinnier if the value of a is a fraction, a proper fraction, something less than 1 but also greater than a 0. And it's exactly the opposite if you have the factor being multiplied directly on the x inside of the function. So you'll see lots of examples of this in your homework, and you'll be able to tell the difference after enough practice. Now, if we're talking about reflections over the x-axis, that's going to be negativity imposed on the function output. If it's negativity imposed or the opposite imposed on directly on the x, then it's reflection about the y-axis, okay? And this, of course, in this last column outlines the functional change that goes on. And then also the physical change in the picture is the draw the graph of f and column right here. So hopefully you have this summary of graphing techniques at your disposal while you are practicing doing homework, so that you can reference this as you learn. And then if you have enough practice, you will have internalized this information, and then you won't need to reference it. And that's hopefully how you will arrive once you, what's the word I'm looking for? Feel like you're prepared for our first exam. Okay, great. So I have a series of exercises. Let's go ahead and find all of the visual representations that go along with A through L functions, okay? Or graph, match the graph. They're not necessarily, oh, are they all functions? It looks like they all pass the vertical line test. Yes, they are, but they are not using function notation for seemingly an unknown reason. Okay, so let's go ahead and I'll change the color to orange so it really pops against this blue. And let's start with y equals x squared plus 2. So x squared, that's a parabola. It's upward facing, I know, because there's no coefficient of negative in front of the x squared, and then it's shifted up by 2 units because this plus 2 is outside of the function itself, the x squared. Now, if it was x plus 2 quantity squared, that would be different. That would be a horizontal shift. So this one's clearly vertical and up by 2. So I would say that number 12 appears to be emulating that right there. So I'll say 12 is A. Cool, and I'll knock that out. B, let's go negative x squared plus 2. So this is still a vertical shift of 2, but we've got to flip that parabola upside down by virtue of this negative 1 factor in front of the function, okay? So that'll look like which one? Which one's upside down and looking like shifted down by 2 units. It looks like, or up by 2 units rather. Sorry, this one's upside down and up by 2 units, right? So this one will be B. Boop. C, it's going to be an absolute value, but shifted up by 2. Okay, so that's your V. Absolute value of x is that V-shaped business, but up by 2. I'd say that that looks a lot like 14, so I'm going to say that one's C. Boop. D, we have an upside down V by virtue of this negative absolute value, and then shifted up by 2. So where's my upside down V shifted up by 2? That'd be this one right here, so this one's our D. Boop. E, y equals the quantity x minus 2 squared. So this is a horizontal shift 2 units to the right. Okay, and why am I saying it's horizontal? Because this added or subtracted value is directly imposed on the x inside of the function itself. So, and again, minus 2, it's actually movement to the right. So I'm going to look for a parabola who's moved over 2 units to the right from the origin as far as its vertex concerned, and that's going to be number 8. So that's E here. Boop. F. Now, this one's going to be shifted 2 to the left, and then upside down parabola. So where's an upside down parabola shifted 2 to the left? It looks like I'm at number 15 right there. So that'll be our F. Up. Great. G, we have an absolute value, but it's a horizontally shifted 2 units to the right. Okay. So that'll be 2 units to the right. Aha. There we go, with the little v. So that'll be 17 is G. Boop. All right. H. we have a 2 units to the left and upside down V. 2 units to the left and upside down V. That's number 9. That's H. That's my H. Boop. All right, I is, ooh, an x squared, so a parabola, and it's still upward facing, but it looks like, since there's a 2 multiplied on the function, that it will be compressed. Okay, so we're looking for a skinny parabola. Okay, so ooh, this one looks pretty skinny to me, right? So notice that as I go out 1, if I plug in a 1 for x, then I have an output of 2. So that appears to be on the graph itself, and it's skinnier than most of these other parabolas that we've seen from the parent function. So I would say that number 11 is I. Cool. Now, same type of skinniness involved with the, or compression rather, with an x squared, but it's going to be upside down. So look for an upside down skinny parabola. I think that's number 16 right here. That's J. Boop. And K, y equals 2 times an absolute value of x. So this is going to be a V, but it's going to be, you know, compressed by a factor of 2. So we're looking for a skinny V, skinnier V, that looks like this right here. So there's K. And lastly, I mean, we can go by process of elimination. We have a skinnier or compressed V shape, but it's upside down. That's going to be our 13, and luckily that's the last one that's left. All right, great. So this concludes my lecture. And you're going to have plenty of questions on other types of problems that I did not cover in lecture, and that'll be good fodder for our discussion in class. So definitely come to class if at all possible with your questions that you've been working on for the homework for these sections, and we'll tackle those as they come, and we'll do more exercises in small groups as well. Great. See you very soon.